webcast. We're going to talk about the 1.15 release that includes geospatial queries. This release has been in development for about 4 months, so we're very, very proud and happy to be able to ship it to you and give you the opportunity to play with the features. And we're very excited about telling you what you could do with this release and what kind of applications it lets you build. So the way we're going to do this is Ryan Paul, a developer evangelist here at RethinkDB, is going to give you a demo of some of the commands and give you, just a couple of examples of how you can quickly and easily start using these features. And then he'll show you a really exciting example app that uses RethinkDB geospatial features to do some really, really cool stuff. So if you guys have questions, please feel free to ask anytime in the chat. And then once Ryan is done with his demo, I'm going to do a little bit of an FAQ and answer some of the questions that might come up. Okay, so without further ado, let me introduce you to Ryan Paul, and I'm going to give him the floor.
Hi, I'm Ryan Paul. I'm really excited to be sharing our new geospatial features with you. We just released RethinkDB 1.15 today, and that's the release that introduces all of these new features. We have geographical types that allow you to define spatial geometry, and we have support for geospatial queries. So what these features do is they really lower the barrier to building smarter location-aware applications. This is particularly exciting, if you're building like anything from consumer-facing mobile software to, like a GIS research platform. These features will really help boost your productivity. Location awareness is really, really exciting capability, especially when you look at what you can do on mobile devices where every smartphone has GPS built in. You can provide all kinds of contextually relevant information based on location. So I'm here to show you a little bit of how these features work and what you can do with them. So geographical types, you can create points, lines, or polygons. And basically these correlate with positions on a map. The underlying data representation uses GeoJSON, which, as the name implies, is a standards-based JSON format for describing geometries for mapping. So I'll show you real quick what a point looks like. We're putting in our coordinates here, and you'll notice that there's just two values, longitude and latitude. Longitude comes first, which is a convention from GeoJSON that we've adopted that we support in our query format here and all of the commands. So our point, what this does is it creates a point in space. And the longitude and latitude I've inputted here actually roughly Tokyo, the location of Tokyo on a map. So you can see here what the point looks like in the output. We have this geometry type and coordinates. So that's very simple. A point is the most basic atom, if you will, of geolocation. So now you can also do something a little more sophisticated. Let's clear out the point and create a circle. A circle, you start with a point, which is the values that we have in the array there, and then you specify the radius, which in this case is 350 miles. And you see we have those optargs there. We specify that the unit is miles. You can use whatever you want, meters, kilometers. In this case, we're just creating a circle that's 350 miles around Tokyo as the center point. In GeoJSON, there isn't actually a construct of a circle. What it's doing is creating a polygon that kind of approximates a circle. You can see here what that looks like. The coordinates here, these are all of the points that make up a polygon I believe, a 33-sided polygon that emanates from Tokyo. So once you've got your circle, let's say that you wanted to perhaps find a point that intersects with it, or see if a specific point in space intersects with it. So let's try a point. So we have this intersects command here that we attach to the circle. And the point I've specified here, the second point, is it's Osaka, which is definitely within 350-mile radius of of Tokyo. So when we run this query, it's going to tell us the answer is true. So you can see it's pretty easy to work with these types, and the way that they interact with each other is fairly intuitive and straightforward. Let's say that you wanted to, for example, compute the distance between Tokyo and Osaka. We can try another query. So we're going to use the r.distance command, and we're going to specify 2 points, and then we're going to pass the option there to say that we want the output to be in miles. So let's run that query. And now you can see we've got the distance between 2 cities as computed. So I mean, that's great and all. We've got all of these points and shapes, and we're looking at intersections and distances. But the real magic is when you start to put this data into a database and perform queries against it. So to give you an idea how that works, I'm going to take a data set that's kind of interesting, and I'm going to show you how to perform some geospatial queries against it. The data set in question that we're going to play with here today comes from the USGS. They provide a feed of earthquake data. So let's input that. So those of you who caught our last webinar, you probably are already familiar with the r.http command. What that does is it fetches data from a remote server, based on an address, and it lets you just drop it right into the database or work with it in the database context. So we're going to use the r.http command to grab this JSON feed from the USGS, and what this feed contains is every single earthquake for the past month that has a magnitude of 2.5 or higher. So we're just going to run that query so you can see what the data looks like. You can see here that each of those earthquakes, we have like properties here with some metadata, and we have geometry, which specifies a point, the location at which the earthquake took place. This is sort of GeoJSON, but they're using like non-standard. They have a third value here, which I think is probably altitude. But here's the longitude and the latitude of this particular earthquake, and you can see here there are all of these different earthquakes in the data set. What we're going to do is insert that data into our RethinkDB table and start doing queries on it. Now to get it into the table, what we want to do is take that geometry property and transform it into a point. That way, when we store the data, we can query against it as though it's an actual geographical type. So I'll show you how to do that now. We're going to use a command called merge. Now what the merge command does is it allows you to modify or add properties to a set of objects, to every object within an array essentially, or a set of objects. So we're going to take our earthquake data and we're going to use the merge function to basically iterate through every single one of these earthquakes and replace the geometry property with a point object created with the r.point command, where we're passing it the longitude and the latitude as the parameters. So I'll run that now and you can see what that looks like. So here we go. You can see now that our geometry property is a proper RethinkDB geometry type. Now we're going to insert that into the database. It's relatively straightforward. We're just going to wrap the whole thing with insert. And put a closing paren at the end. So now this is going to take all of those records and put them in the database. And you can see here we inserted about 1,100 records here. Those are all of the earthquakes for the last month. Now we want to query it, but before we can query it, we have to create an index. Well, first here I'll show you what it looks like in the table. You can just see that all the data is there. There you go. So now we're going to create an index so that we can perform a proper geospatial query. You can use the filter command and to perform geospatial queries without using an index, but the index is obviously going to improve the whole experience a bit. So let's do index create. We're going to use the property geometry, and we're going to set geo to true. Now that geo true option there is really important. If you just created a regular index on the geometry property, it would just be a regular index. So I mean, you could do index queries against the coordinates or something, but it wouldn't be it wouldn't let you do actual geospatial queries. By specifying geo true, you're indicating that you want to create an actual geospatial index. So let's do that now. So we've created our index, and now we can perform geospatial queries against that index. So just as an example here, let's try and find all of the earthquakes that occurred within 200 miles of Tokyo. We're going to use a get intersecting command and create a circle here with a radius. And in our get intersecting command, we're going to specify that the index we want to perform this on is that geometry property. So now we have 12 rows returned, and these basically represent all of the earthquakes within 200 miles of Tokyo. You can see here from the metadata that these are all in Japan as expected. So that's pretty straightforward. It's really easy to work with this stuff, and what you can build with it is pretty exciting when you get into the details. So I'd like to show you like a real-world example, an actual application that I built from scratch, that takes advantage of these features and this data set. So this is the RethinkDB earthquake map, and what you're looking at is all of the earthquakes that took place over the last 30 days, from that data set, and I've plotted them all on a map. So the back end for this application is just a really simple Node.js app built with Express with a few simple API endpoints, and of course all the data is stored in RethinkDB. On the front end, I've built the user interface with AngularJS, and I used a library called Leaflet for the map interface. Leaflet makes it really easy to create interactive maps where you're setting points and markers and things like that, and it can use OpenStreetMap tiling to give you a really nice vector map look. So here's the map. You can see all of the points, and we have a list on the left-hand side here, all of our earthquakes, and when you click an earthquake, it'll zoom in and it'll show you where it is on the map. And you can see some of these circles are bigger than others. The size of the circle, the radius, is based on the magnitude of the earthquake. So we can flip through a few earthquakes here and you can get an idea. And that's pretty cool. It's an interesting visualization. It gives you an interesting sense of where the earthquakes are taking place. You might have also noticed that we have our little thinker here. That's the thinker. It's our RethinkDB mascot, basically. And he's sitting here in Southern California hanging out. And the reason he's here is because that's where I am. What I've done here is I've used the browser HTML5 geolocation APIs to have the browser determine my location and then plot where I am on the map. You can see in Chrome here that we have the little signal in the URL bar that shows that the page is tracking my location. So what I wanted to do to take advantage of geospatial queries here is have it identify the earthquake that's closest to my location, which is going to be, right over here. So down here in the list, I believe it's a little further down. Yeah, you'll see here that we have, this red text on the earthquake that correlates with the one that's closest to my location, and it tells me the distance, 357.9 miles. So there we go. That's done with a RethinkDB or a requel command called getNearest. So I'd like to show you what the source code looks like on the back end. This is, like I said, it's just a simple Node.js app written in JavaScript, of course, using Express.js. You can see here this is the query that loads the data from the remote data source and puts it in the database. We set up the table and the index and all of that. And here's a set interval where we're doing like automatic refresh, so it'll pull in new data every so often. And then down here we have our two API endpoints that we've defined. The quakes endpoint, basically it just gives you a list of the earthquakes ordered by magnitude. So if you were to type quakes in the browser, you can see the output of that API. It's just returning the earthquake data. Now, down here is where the real fun happens. We have this API endpoint /nearest. And what that does is it returns the earthquake that's closest to the position specified by the user. It takes two parameters. The user passes their latitude and their longitude. And then we take those and we perform a query. So you can see the query right here. We're using the getNearest command, and we're taking the longitude and latitude values and putting them into a point. We're using parse float here because when you get those parameters out of Express, they're strings. So you could use parse float, or you could just put a plus in front of them to coerce them into number. And once you've created the point, you just do a simple query here against the geometry index and specify a maximum distance. So what we're doing is finding the nearest earthquake that's within 1,000 miles of the user's position. And if there wasn't one within 1,000 miles, it would just return an empty array. But for the purposes of this demo, because I have one close to me, it's going to return an actual object. And what it returns is the distance and then the earthquake object itself, which we can put into the map. So that's fairly straightforward. And then on the front end, all we're doing in our Angular side is doing an HTTP GET operation to retrieve the data from the endpoint, from the API endpoint. So I'll show you that real quick, what the front end looks like. You can see here we go, fetching the quakes right here. And then, yeah, so it's just plotting each one in the map. And we've got like a watch on the array so that we can add and remove the individual points as needed when the array gets filtered. So like we have in our map, we have like a little date selector that you can use to select a specific date if you only want to see the earthquakes from those dates. And whenever that changes the contents of the earthquake array, the map will automatically add and remove points. And now finally up here we have our user location. We are using the browser geolocation APIs. That's, where did that go? Here we go, get current position. So this uses the browser HTML5 geolocation APIs to get the coordinates. And once we've got the coordinates, we call HTTP GET, and we go to that nearest endpoint so that we can get the closest earthquake. When it returns it, we just handle it and make sure that we set some properties in our scope so that it can show up in the list. So, I mean, that's about it. You can see there's not a lot of code here that you need in order to accomplish these things. It's fairly straightforward. These features are included in the 1.15 release, so you can get started with them today. You can download RethinkDB, the latest build, from the website, and start working. This specific example is on GitHub. So if you go to RethinkDB on GitHub, you can see we have earthquake map. And this is where you can find the sample code. Yeah, so Slava's asked if I could show the get nearest command in the Data Explorer so you can see what the output looks like. Yeah, so let's take let's do Tokyo for our example here. So let's create a point. All right, so you can see here the nearest earthquake from Tokyo. Yeah, so like I said, pretty simple. So does anybody have any questions? Okay, so we have a question. What if you wanted to get the last 3 closest, or more than one? So you could do. I think what would be the most practical thing would be to get, say, all of the earthquakes within a certain radius. Like you could do intersects command to get everything within 200-mile radius, and then you could do like r.distance on all of them in a map function and find the one that's like order them by distance, say, and then get as many as you would like, if that makes any sense.
Hey guys, this is Slava. I hope you can hear me. So I think our organizer Christina just transferred the screen to me. So I was actually so Ryan started answering the original question, and I think we're gonna go back and forth between Ryan and myself. But what I wanted to do is I wanted to open Google Chrome and show you the API documentation for the get nearest command to answer the question, what if you wanted to do? What if you wanted to get, for example, 3 earthquakes next to you, not just one. So let's look at get nearest. I'm gonna see that here. So I am on rethinkdb.com/API. And what I'd like to do is look a little bit at this command. So the get nearest command actually accepts quite a few optional arguments. And Ryan, he has shown you the basics of some of the commands, but a lot of them can get quite sophisticated. So specifically with get nearest, you can specify here max results, how many results you want, unit of distance, things like that, and maximum distance. So you can actually use the command to say, give me at most 50 earthquakes within a 1,000-mile radius of a given location. And actually, all of the commands, like get nearest, intersection, polygon intersection, stuff like that, are pretty sophisticated. So most of the common operations you might want to do, you should be able to do. And one example of how we thought about this when we were designing the API is, imagine you're building a mobile app and you're building something like Yelp, where you wanted to say, give me all the restaurants, within a 5-mile radius of my location, and maybe limit it to some amount. And you should be able to do all of that pretty easily with the geospatial commands. Okay, so give me just 1 second. I'd like to look at some more questions that people asked. Okay, so Gray actually pointed out that you could say max results equals 3. And then, okay, so Jason asked, is it possible to refine the granularity of the polygon returned for a radius? So Jason, I think you're asking about, so Ryan mentioned at the beginning that if you create a circle and then say, give me everything within that circle, the circle is actually a polygon that approximates the circle construct. It's not an actual circle because most geospatial libraries don't support that. So let's actually look at that. And I'm going to go back to the API page and scroll down here to the geospatial part. And we have a circle command. So let's take a look at that. And the circle command, just like I mentioned, was get nearest. The circle is also pretty sophisticated. You could specify all kinds of things. Specifically, you could specify num-vertices. And num-vertices lets you be as precise or look at the level of detail of the polygon that approximates the circle. So actually it defaults to 32 vertices, but you could set it to something as large as you like. And the larger the number of vertices, obviously the more precise the circle is, but the more sophisticated the intersection commands are, so it just takes a little bit more computation time. Okay, and then DJ pointed out that max results lets you set it to the number you want. Let's see, does anyone else have any more questions? I'll just give you guys a minute in case someone wants to ask a question, or if you just wanted to hop on and say something, you're welcome to do that too. Give me 1 second. Someone said you guys thought about everything. Not everything. So actually someone pointed out on Hacker News, they asked about the number of dimensions that you could use with the system. And of course it was designed for location-aware applications and making those easy, so we support 2 dimensions. And someone pointed out that the Earth, of course, also has altitude. And RethinkDB doesn't support that, although pretty much no other commercial database product supports that either. But there's definitely more interesting things that we could do. So thank you for the compliment, and we're looking forward to extending this feature set as we learn more about the kinds of applications you guys want to build. So Michael asked me to talk a little bit about some of the other features in RethinkDB 1.15. And actually what I'd like to do now is switch to the blog post announcement. And the blog mostly talks about the geospatial stuff. But actually there are two more important features. So there's actually over 50 enhancements in the release. But the 2 major ones that are really worth noting is, I'm going to scroll down here. The first one is performance of certain queries. So let me find that here. We've got a faster queries part. So the way that worked, we actually had a user who used RethinkDB for a particular data set and a particular set of queries, and they discovered they submitted a bug report saying their performance is too slow. So when we investigated, it turned out that RethinkDB wasn't performing optimally on some types of analytic queries. So in particularly what happened was that we used to store, when we look at the layout of the documents as they're stored on disk, we used to have to serialize and deserialize them eagerly. So anytime you access a document, even if you access, a single field, we would load that from disk and deserialize the entire document. So what we've done in the 1.15 release is this serialization and deserialization process now happens lazily. And that can cause just absolutely enormous performance boosts. So for that particular data set and those particular queries, that user saw something like a factor of 40 performance improvement. So their queries went from minutes to seconds, or actually in that case it was hours to seconds. So this is a huge deal, and it will impact most queries. So for most queries that you normally do, you should see about a 15% performance improvement. But for some queries, specifically if you're doing something with analytics, you should be able to see an absolutely huge performance boost, probably about an order of magnitude. And we're careful here, not to put graphs, because we've done a lot of like ad hoc performance testing and a lot of pretty sophisticated performance testing. But what we're going to be doing is building more sophisticated scientific performance tests, because it's an enormous amount of work, and soon we'll be publishing very precise, well-researched graphs of how RethinkDB performs on different types of queries. And so John just said, in order for this performance to be seen, all documents have to be updated. That's actually a great point. So there are some parts to RethinkDB, like when we change the file format, in order to do seamless migration, like if you use RethinkDB 1.14, you have your data file and you install RethinkDB 1.15, it's going to continue to work, and it's going to run things, you're going to be able to run queries on the old data set. And then what the system does is anytime you update a document, it lazily updates it. It lazily updates the format in disk. So, if there are some old documents in your database that you're not going to touch for a long time, they're going to remain in the old format, and when you read it, it's of course still going to work. And anytime you write to them, they're going to move to the new format. And all of this is completely transparent. And some of the features, specifically performance improvements associated with changes in the data format, you're not going to be able to see unless you update the documents either lazily or you dump data and restore it back into the new version, because when you do the restore, it uses the latest format. So John, I'm actually not entirely sure whether this particular performance optimization requires you, either to lazily update the documents or to dump and restore data. I don't think it does, because this was not, as far as I know, a change to the data format. This was more a change in the way the data is interpreted at runtime. So I think you should be fine. But if you want to be sure, you can dump and restore data. And it's a great question. I'm going to ask some of the engineers here that worked on this feature, particularly Daniel and Mark, and I should be able to get an answer. And we'll post it on Twitter. So just one more interesting feature in this release, we added a command called r.uuid. And as you know, if you start RethinkDB and you insert a document and don't provide an ID, RethinkDB will generate one for you. Now we just expose that functionality via an r.uuid command. And this isn't something I think a lot of people will need, but in some situations, some users have asked for it, and this is really, really useful to them. So just so you know, if you need this kind of a command, it's available. Okay, are there any more questions? I'll give you guys a minute in case someone wants to ask something else. Okay. I don't think there are any more questions. Thank you, everyone, for joining the second webcast. Thank you, Ryan, for giving us the demo of the commands and of the application. We're going to be doing a blog post with a full write-up that Ryan did for his application, so you guys will be able to learn a little bit more about how it was done and build apps like this. So thank you very much for joining. We're super excited and proud of this release, and we're really looking forward to seeing what you guys build with it. So thank you, and Another thing I'm looking forward to is doing another one of these for 116. So hopefully this is going to happen, in about 3 to 4 weeks from now. And we'll be posting about it on Twitter and meetup.com and, all the channels. So we're looking forward to seeing you guys soon again.